Here is the problem. We are given a state space model. The state derivative x dot equals the matrix A times the state x plus the vector B times the input u. Here, A is a 2x2 matrix with rows 4 and 2 in the first row and 0 and -3 in the second row. The input vector B is 1 and 0. The output y equals C transpose x, where C transpose is 2 and 3. We need to answer 3 questions. Part A, is the state space model stable? Part B, is the system BIBO stable? Part C, for a different transfer function, g of s equals s plus 4 divided by s cubed plus 2s plus 1, apply the Routh-Hurwitz criterion. Part A, check internal stability of the state space model. A state space system is stable when all eigenvalues of A have strictly negative real parts. To find the eigenvalues, we would normally compute the determinant of Si minus A. But here A is upper triangular. The lower left entry is 0. For a triangular matrix, the eigenvalues are simply the diagonal entries. The diagonal entries are 4 and -3. So the eigenvalues of A are lambda 1 equals 4 and lambda 2 equals -3. The eigenvalue 4 has positive real part, that is in the right half plane. Conclusion, the state space model is unstable. Part B, check BIBO stability. BIBO stands for bounded input, bounded output. A system is BIBO stable if every bounded input produces a bounded output. BIBO stability is determined by the transfer function, not directly by the state space model. We need to derive the transfer function from the state space, then check its poles. The formula is g of s equals C transpose times the inverse of Si minus A all times B. Let us compute this step by step. First, compute Si minus A. Si is S times the identity matrix, which has S on the diagonal and 0 elsewhere. Subtracting A, we get a matrix with S minus 4 in the top left, -2 in the top right, 0 in the bottom left, and S plus 3 in the bottom right. Next, compute the determinant. For a 2x2 matrix, the determinant is the product of the diagonal minus the product of the off-diagonal. The diagonal product is S minus 4 times S plus 3. The off-diagonal product is -2 times 0, which is 0, so the determinant equals S minus 4 times S plus 3. The inverse of Si minus A is the adjugate matrix divided by the determinant. The adjugate swaps the diagonal and negates the off-diagonal. We get S plus 3 in the top left, +2 in the top right, 0 in the bottom left, S minus 4 in the bottom right. Now multiply this inverse by B, which is the column 1 and 0. The result is the column S plus 3 over the determinant and 0. Finally, multiply C transpose, which is 2 and 3, by this column. 2 times S plus 3 over the determinant plus 3 times 0. So g of s equals 2 times s plus 3 divided by s minus 4 times s plus 3. Notice the factor s plus 3 appears in both numerator and denominator. It cancels. G of s simplifies to 2 divided by s minus 4. This transfer function has a single pole at s equals 4. The pole at +4 is in the right half plane. Conclusion. The system is not BIBO stable. Side note, the cancellation tells us something deeper. The eigenvalue -3 appeared in A but not in the transfer function. That mode is called an uncontrollable mode. The input B cannot reach it. The transfer function only sees the part of the dynamics that is both reachable from the input and observable at the output. Part C. Apply the Routh-Hurwitz criterion to a new transfer function. G of s equals s plus 4 divided by s cubed plus 2s plus 1. The denominator is s cubed plus 2s plus 1. Notice that the coefficient of s squared is 0. This is going to cause an unusual situation in the Routh table. Let us see how to handle it. Build the Routh table. For a third-order polynomial, the first row is s cubed with coefficients 1 and 2, the coefficients of s cubed and s. The second row is s squared with coefficients 0 and 1, the coefficients of s squared and the constant. We have a 0 in the first column of the s squared row. The standard Routh formula would divide by 0, which is undefined. The trick is to replace the 0 with a small positive number epsilon and take the limit as epsilon approaches 0. The S1 row has one entry in the first column. The Routh formula gives epsilon times 2 minus 1 times 1 divided by epsilon. That is 2 epsilon minus 1 over epsilon, which equals 2 minus 1 over epsilon. As epsilon approaches 0 from above, 1 over epsilon goes to plus infinity, so the whole expression goes to negative infinity. The S0 row simply carries down the constant, which is 1. So the first column reads 1 epsilon negative infinity 1. Count the sign changes. From 1 to epsilon, both positive, no change. From epsilon to negative infinity, positive to negative, one sign change. From negative infinity to 1, negative to positive, another sign change. Total, 2 sign changes. By the Routh-Hurwitz criterion, 2 sign changes in the first column means 2 poles in the right half-plane. So the transfer function g of s equals s plus 4 over s cubed plus 2s plus 1 has 2 unstable poles. Conclusion: the system is not stable. Key lesson: a missing s squared term is not a special case you can ignore. The 0 coefficient creates a 0 in the Routh first column, and the epsilon trick reveals hidden right half-plane poles. Let us summarize. 3 stability checks. Part A, internal stability from state space. A is upper triangular with eigenvalues 4 and -3. Eigenvalue 4 is in the right half-plane, so the state space model is unstable. Part B, BIBO stability. We derived the transfer function g equals 2 over s minus 4 with pole at +4, not BIBO stable. The cancellation revealed an uncontrollable mode at -3. Part C, Routh-Hurwitz on a new third-order denominator with a 0 s squared coefficient. The epsilon trick gave 2 sign changes in the first column, meaning 2 unstable poles. 3 stability questions, 3 unstable answers.